Rightio, so this, the lectures today are all going to be on chapter 8 in the notes, so I'm sort of bypassing the lightings chapter, and that's page 139 in your notes. So we're going to be looking at what are called Bezier, I always probably pronounce this wrong, I could say Bezier, I think it's meant to be Bezier. Don't know, any French speakers here? Okay, I'm going to be pronouncing it Bezier, apologies if that's incorrect. Okay, so we're going to be looking at Bezier curves. Bezier curves is sort of a polynomial function. So I'm going to go, just to recap what polynomials are. This should all be old information to you. A polynomial is a sum of a variable raised to different powers and multiplied by coefficients. Okay, so what we have here is you have the sum, your x is your variable, n is some power, and I is some scalar coefficient. Okay, so for example, a0 plus a1x plus a2x squared plus a3x cubed, etc., etc. Okay, that's what a polynomial is. Okay, and we refer to the degree or order of the polynomial as the highest power of your variable. So in this case, this would be a degree n polynomial. And we give them names. Okay, so a degree 1 polynomial, okay, where the highest power of x is 1, is called a linear polynomial. Degree 2 is quadratic, cubic, quartic, quintic, septic. Don't know, anybody Latin? Anybody speak Latin? No. So what is it? Hept. Optic. Would that be 8? I don't know. I'm not a Latin scholar. So okay, so these are polynomials. I'll be talking a lot about quadratic and cubic today. So in other words, polynomials of degree 2 and 3. And one thing to sort of realise, I've graphed a few examples of polynomials here. And essentially what I want you to take from this slide is the higher the degree of the polynomials, the more changes in direction the curve of that polynomial has. So a degree 1 polynomial, straight line, has 0 changes of direction. A quadratic, degree 2, has 1 change of direction. A cubic can have 2 changes, quartic 3. So the curves, or the changes in direction in those curves, is 1 less than the degree of the polynomial, which becomes relevant when we start dealing with what are called B-splines later on. Okay, polynomials use parametric equations. You've seen these. The vector equation of a straight line is a form of a parametric equation. Okay, essentially we have a parameter t, and that parameter t is somewhere in the range 0 to 1. So it's a real number in the range 0 to 1, and we can determine the value of a point on our polynomial curve. Okay, I've split it up in terms of x and y because that's how Bezier curves do it. But you probably, if you think of this as being a vector of x and y, there's a vector of x0, y0, there's a vector of x1, y1. It's essentially the vector equation of a line. You've also seen this in a slightly different form. Okay, in a different form you've seen it in, which we did when clipping. So if we remember we're clipping a plus t, b minus a. So if you've done the assignment 6, you've used this. Okay, well that's also the same as 1 minus t times a plus b. So I could write that in that form. Okay, so that's exactly the same. It's just written in a different form. The reason why I've written it on these slides like this is because the derivation of the Bezier curves uses that form. It's nothing new there. Okay, so that's a parametric equation. So if you've got a straight line, okay, so there's your parametric equation. straight line joining points P0 and P1. Okay, and this value of t is somewhere in the range 0 to 1. So when t is 0, we have 1 minus 0, which gives us 1 times P0 plus 0 times P1. So essentially, our point on our polynomial line, our point on our line when t is 0 is at P0. If I increase t to be, for example, a quarter, so we'll have 0.75 times P0 plus 0.25 times P1, and we're a quarter along the line between P0 and P1. A half, so we're halfway along the line, half of P0 plus half of P1, and when t is 1, we're at P1. Okay, so t between 0 and 1, when t is 0, we're at the first point, when t is 1, we're at the second point, when t is somewhere in the middle, we're somewhere in the middle. So that's sort of just sort of the basics behind parametric equations, and especially the parametric equation for the straight line. Okay, so this brings us on to Bezier curves. Now, in computer graphics, up till now, we've been dealing with a lot with polynomials, a lot with straight edges. Okay, well, computer graphics, there's lots of applications where you don't want straight edges, you want nice curves. Okay, so and this is where Bezier curves come in. And it's essentially a way of drawing smooth curvature lines. Developed in the 50s, was it? I think it was around about 50s or 60s by the car manufacturing industry. Pierre Bezier, who it's named after, was designing cars at Renault. But it was actually another guy, Paul de Casta, again, probably pronunciation's rubbish there, who actually 3 years before that invented it. But Bezier's got his name on it, so he's happy. De Casta is not as well known. One of those things in mathematics, a lot of people, things in mathematics are discovered around about the same time, and whoever gets their name on it, they're just lucky. Common applications, computer-aided design software. So if you're designing a car, I don't know whether you've seen any sort of old cars from the 60s, very box shaped. Okay, more modern cars tend to be curves. Okay, so common applications of design software, 3D modeling, and typefaces. So when you type something on a computer, typefaces are, or the fonts, they are defined using Bezier curves. Now what we have with the Bezier curve is we define it using a small number of what we call control points. Okay, and we can have different degrees of Bezier curves. So an n-degree Bezier curve is defined using n plus 1 control points. So if you want a quadratic curve, which is degree 2, you need 3 control points to define it. And what we do is we can apply translations, rotations, scaling, translations, etc. can be applied to the control points. Okay, so we've only got a small number of control points, so we've only got a small number of translations which need applying. And then when we apply the translations to control points, then we can generate the Bezier curve from those translated points. Here's an example. This is one I did in MATLAB. Basically, I printed out a large Times New Roman S, and I sort of like a bit of trial and error. I tried to match the control points to what the S would look like. Okay, so what I have here is I've got a load of red circles. Now these are control points. Now this is actually a cubic Bezier curves, or there's lots of cubic Bezier curves. So each cubic Bezier curve is defined by 4 control points. So for example, here, if you look at these 4 points here, okay, that could have been used to define that curvature. So these 4 here could have been used to define that curve. So there's lots of different Bezier curves that have gone into generating this S. And then I've just joined them all together. Okay, what I've also done here is, I haven't had to sort of work out where all the control points are. All I've done is I've taken this S and scaled it and translated it. Okay, and then that allows me to resize my font, which is exactly how sort of word processing programs work on a computer. The blue line, by the way, is the Bezier curve, and that's generated from those control points. Okay, so let's have a look at the derivation. So what we have here is, I want to derive a quadratic Bezier curve. So quadratic is degree 2, so I need 3 control points. So I've got P0, P1, and P2 on my 3 control points. Now, what we do is we find positions of 2 other points, Q0 and Q1. Now, Q0 will lie on the line between P0 and P1, and Q1 will lie on the line between P1 and P2. Okay. So and remember, we're using parametric equation of a straight line here. When t is equal to 0, my Q0 is at P0, and my Q1 is at P1. So that's t is equal to 0. Let's increase t a bit. So t is now 1/10. So Q0 has gone 1/10 along this line, and P1 has gone 1/10. Q1 has gone 1/10 along this line, and I've drawn the blue line between them. What I've also done is the black blob here. That is 1/10 of the line joining Q0 to Q1, and I've drawn a black blob there. Okay. When t is 0.2, Q0 is a fifth along this line between P0 and P1, and Q1 is also a fifth along that line between P1 and P2, and I've drawn the black blob, which is a fifth along the line between Q0 and Q1. And we keep going. Okay, so I increase the value of t, Q0 moves along the line between P0 and P1, and Q1 goes along the line between P1 and P2, and that black blob is the same along the line between Q0 and Q1. Okay, so now I've got 10 or 11 blobs, and if I draw a line through the blobs, you can see I've got a nice curve, which is essentially what you did with the first activity at the start of the lecture. Okay, that is a quadratic Bezier curve. Okay, so let's have a look at the sort of algebra. Okay, so Q0 and Q1 are between P0 and P1 and P1 and P2. So using the parametric equation of the straight line, we have these 2 expressions. Now, CT is our point on our curve, and that's between Q0 and Q1. So CT is given by this parametric equation. So what will I do now is, instead of Q0, I replace that expression, and instead of Q1, I replace it with that expression. Doing a bit of simplification, a bit of algebra, and I get this parametric equation here. A few things to notice about this. Highest power of t is 2, so it gives us a degree 2 or a quadratic curve. P0, P1 and P2, they are our control points, so we know what they are before we draw the curve. T, how many values of t we take will depend on how smooth our curve looks. If we take only a few values of t, it'll look jagged. So essentially, we're still drawing straight lines between those points on our curve. So the more values of t you have, so t maybe 100 values between 0 and 1, the smoother your Bezier curve will look. Okay, so that's the derivation of a quadratic Bezier. Now, this derivation process is known as de Castigel's algorithm, after Paul de Castigel. He sort of formalized it. So let's say we wanted higher order Bezier curves. So we're going to introduce a slight change in notation here. So we're going to say that P, I, J are control points. When j is 0, we have our original control points. So if I go back to this one, P0, P1, and P2 are our initial control points. Okay. When j is equal to 1, we have what we call the first level control points. So those are our Q values. Okay. And then when j is equal to 2, we have our value on our curve. Okay, so pi0 are your initial control points, pi1 are your q values, and p02 is your value on the curve. And this is the algorithm. Okay, so think of it as like the I and J notation as being a matrix. Okay, so I goes down. Okay, so these are your control points going down, and going across is your level. Okay, with a quadratic, you just got P, Q, and your curve. Okay, and the Casta came up with this triangular scheme. Okay, so the value, and remember these will be coordinates. Okay, the value of this Pij is a combination of Pij minus 1 and Pi plus 1 j minus 1. So let's say that was P0 and P1, that will give us Q0. Okay. So the horizontal arrow, that denotes the coefficient 1 minus t, and the diagonal arrow just denotes the coefficient t. So we're going to have a look at the same derivation but using that scheme. Okay, so if I change this to ij notation, so that was P0, but now because it's on J is on the 0 level, that was P00. That was P1, but again, it's the initial control points, that's P10, and that was P2. What was Q0 is now P01. Okay, so that was Q0, but we're on the sort of next level. Okay, so when J is equal to 0, you're on the original control point. When J is equal to 1, you're on the next level. Okay, and the same with Q1 is now P11, and our point on the curve is P02. So the 2 represents what the degree of the Bezier curve is. Okay, so that's the full triangular scheme. So those are your 3 initial control points. 2 of them combine to give you this control point, P01, and the final 2 combine to give you P11, and those 2 combine to give you your point on the curve. Okay, so starting at the right, that's our point on the curve. Horizontal arrow represents the 1 minus t coefficient. Vertical arrow represents the t coefficient. Okay, so if I replace P01 with its parametric equation of a straight line, and do the same with P11. Okay, so doing a bit of simplification. So we've got 1 minus t times 1 minus t is of course 1 minus t squared, and you have 1 minus t times t, and you have 2 lots of those. Okay, so we've got 2 lots of t, 1 minus t. Okay, so that's derivation of the quadratic Bezier curve. When you start to get higher order degree curves, it starts to get more and more control points coming in. So here, I've got a cubic Bezier curve, so I've got 4 initial control points, P00 up to P30, so the red ones. The blue ones are found between the red ones, the green ones are found between the blue ones, and finally our point on the curve is found between the 2 green ones. Okay, so it's the same process, we just got up to another degree. So that's your triangular scheme here. Again, starting with your curve. Okay, so point on our curve is found somewhere between the green control points. If I replace the green control points with the equation of a straight line between the blue control points, and I replace the blue control points with their corresponding ones from the red control points, you can see it's starting to get a little bit unwieldy. It's starting to get a bit too big. It's not difficult algebra, but it's a little bit too big. And eventually, if I do a bit of cancelling out, a bit of manipulation, we get down to this expression here. So you notice we have the 4 control points. That should be P2, 0 there. Okay, and the highest power of t is 3. So it's a cubic. Okay, so that's a cubic Bezier. What if I wanted a quartic, or going higher in degrees? It starts to get a little bit messy. Fortunately, there is a pattern to the coefficients. And that pattern is in the form of what we call Bernstein polynomials. Okay, so this is a general form of a degree n Bezier. Okay, so you say, okay, let's say I want a cubic Bezier, so n is 3, and my curve is defined by the sum of I equals 0 to n, in my example would be 3, and I have this function here, bin, and that's a function of t. That's called a Bernstein polynomial. And that's multiplied by pi, which is a control point. Now the Bernstein polynomials is given as this, so it's a function of t, and it has two parameters in that function, I and n. Okay, this here, just sort of like confuse the notation, this is the binomial coefficient. It's not a vector or a matrix. That's n choose I. How many ways of choosing I objects from a list of n? Okay. T is your parameter. Well, that's just going to be a function. So then t to the power of I, 1 minus t to the power of n minus I. So just to quickly talk about binomial coefficient. Okay, that's written as n over I. Some people do sort of NCI or NCR, something like that. This is a binomial coefficient, and it's a number of ways of choosing I items from a set of n. So it's to do with combinatorics. And that's how you calculate it. Okay, I never remember that. Okay, I use Pascal's triangle. It's a lot easier way of calculating binomial coefficient. So, for example, if I had, let's say I got my cubic, so n would be 3, and I'd be summing from 0 to n. So if n is equal to 3, I would be 0, 1, 2, and 3. So I've got 4 Bernstein polynomials to calculate. And my 4 binomial coefficients would be just reading across that line, that horizontal line in Pascal's triangle. I take you all know Pascal's triangle. The number is the sum of the two numbers above it. Okay, so for my example of a cubic Bezier, that's my Bernstein polynomials. Okay, so I have I going from 0, 1, 2, and 3, and n is of course 3. So 3, 2, 0 is just 3, 2, 0 is just 1. T to the power 0, that's going to be 1, because anything to the power 0 is 1. And then 1 minus t to the power 3 minus 0. That obviously simplifies to 1 minus t cubed. Okay, n choose 1 is 3. T to the power 1 is obviously t. 1 minus t to the power 3 minus 1 is 1 minus t cubed. That's squared, sorry. Okay, so we can calculate quite easily what these Bernstein polynomials are, and I've got 4 of them. Now these are each multiplied by the control points P0, P1, P2, and P3. That's a very easy way of calculating the general Bezier curve. Okay. So in fact, we don't have to go to Casta's algorithm. Okay, we can just do it using Bernstein polynomials. I have taught you this, going back to here, I have mentioned this for a reason, because it's important when we go on to talk about B-splines. Okay, so these are Bernstein polynomials. These affect the behavior, or these basically give how much of an effect does each control point have on the Bezier curve at that point. So what I've done here is I've graphed the Bernstein polynomials against t. So remember, t is our parameter in the range 0 to 1. And for the quadratic Bernstein polynomials, I've only got 3 of them, and I've graphed them here. So the blue one, that's what's multiplied by the first control point, t0. The red one is what's multiplied by the middle control point, and the green one is what's multiplied by the last control point, p2. So when t is equal to 0, we're all about the first control point. As we increase t, the amount of the effect that the first control point has on the curve decreases as the other two increase. So as we go up in t, so we get to a point here where the middle control point has more of an effect on our curve than the first control point. If we bounce back in the middle, you can see that the middle control point has most effect, with the two end control points having equal effect. And as we go up to t, eventually the final control point will take over. Okay, so that's the behavior. That's how those Bernstein polynomials affect the behavior of the Bezier curve. And you can do also the similar, and that's for cubic. Okay, so we've got 4 Bernstein polynomials, we've got 4 control points, and you can see same sort of similar behavior. In this case, when we're in the middle, okay, the sort of middle 2 control points have equal effect, and the first and last control points have pretty much an equal effect. Okay. Everything we do in computer graphics has got to be easy. The reason it's got to be easy is because we're doing it lots and lots of times. Okay. If we were to program our Bezier curves using, going way back here, using this, it's going to slow us down a bit. It's quite a long expression. Okay, and computers are very good at matrix multiplications. So it's better to express our Bezier curves as a matrix equation. Okay. So what we want to do, or what we do, is we express our Bezier curve as this matrix equation. What we have here is we have a n+1 columns in a matrix. Now each of these would be a coordinate. So if you're in 2D space, this would be a 2 by n+1 matrix. If you're in 3D space, this would be a 3 by n+1 matrix. Okay, so each of these are column vectors of the positions of each control point. M is a square n+1 by n+1 matrix. So if you've got a cubic Bezier curve, M would be a 4 by 4 matrix. And finally, we've got a column vector here, which again is an n+1 by 1 matrix. And we have descending order starting from the highest power of t, and we have descending order going down. So that's our matrix equation. The key is, what is n? Trying to find n. Now, your different degree, the Bezier curves will obviously have a different value for that matrix. Now, what I've done here is I've expanded out the coefficients of the Bezier curve. Okay, so here we have, this was t minus 1 squared. This was 2t times t minus 1. Sorry, 1 minus t. That was 1 minus t squared, sorry. This was 2t times 1 minus t, and that was just t squared. So all I've done is I've kept the coefficients there, I've just expanded out those brackets. So what we want is, for the first one, we want t squared times p0. Oh, sorry. So if you look at the t squared, we want t squared times p0. We've got minus 2t squared, and then we've got t squared. So that takes us down. Okay. It always also takes us across. The easiest way to look at it is the first row of the matrix M is the coefficients of t. Okay, so that's 1, minus 2, 1, 1 minus 2, 1, minus 2 and 2, minus 2 and 2. We've got nothing, so we don't have a just a scalar there, so we've got nothing there. And finally, we've got 1 times t squared plus 0 times t plus 0 times 1. Okay, so that is exactly the same as saying that. And similarly, a cubic Bezier curve can be expressed in this way. So 1 minus t cubed is minus t cubed plus 3t squared minus 3t plus 1. And we do the similar. So here we'd have 3t times 1 minus t squared. Okay, and that gives us a coefficient of t cubed, t squared, t, and 0. So that's M for the quadratic Bezier, that's M, the cubic Bezier. Okay, so this is something I'm going to ask you to do for assignment 9. Well, I've actually given you the code here. This is a little function, but given your control points P and values of your parameter T. Now, this T would be a matrix of a vector of values. Okay, so what I do here is I define M, which is this matrix, 3 by 3 square matrix, and I define T, which is this. Now, if you imagine T, let's say I'm using 100 values of T. I've got a row array with 100 values starting at 0, ending at 1. Okay, so what I've done here is the first row is all the values of T squared. Second row is just T, and the third row, well, it's just a row of 1s. But then all I do is calculate the the curve is P, which is a matrix of control points, times M, times T, that's your curve. It's as easy as that. 3 lines, that calculates your Bezier curve. And that's something you'll have to do for the cubic Bezier for your assignment. So this is quadratic. I'm sure you'll see it's not too difficult to go to cubic from there. Okay, right, what I want to do now is just switch to the second activity. Okay, we're going to actually calculate we're going to calculate a quadratic Bezier using that matrix equation. Okay, so a quadratic Bezier curve is defined by 3 control points. I've given you the 2D coordinates of those 3 control points. Calculate a point of the Bezier curve corresponding to the following values. So the first thing which I find helps to do is I'm just going to plot the 3 control points on this grid. Okay, so I've got a control point at 1, 1. I know you can't see that, but there's a control point here. 1 at 7, 5. Which is here. And 1 at 9, 3. Here. Okay, so those are our 3 control points, and I'm just going to draw a line just to represent that, the initial line between those 3. Okay, so our curve is going to be somewhere under here. So the first thing I've asked you to do is, I'm going to have to zoom out a bit to get it all on. I'm going to turn off autofocus. Right, first thing I want you to do is when t is equal to 0.2, I want to calculate all of this. Okay, so what we have is when c is equal to 0.2, the first thing I have is, I have to keep moving up and down. First thing I have is this matrix. Now this will be a 2 by 3 matrix because each of these coordinates, it's got 2 elements in it. So P0 is going to be 1, 1, P1 is going to be 7, 5, and P2 is going to be 9, 3. So first I have 1, 1, which is P0, 7, 5, which is P1, and 9, 3, which is P2. So that's my control points. Well, they are my control points. Next, I'm just going to copy out the 3 by 3 M matrix. And lastly, what I have here is I've got wherever t is squared, t and 1. So 0.2 squared is going to be 0.04. And t is just 0.2, and I've got 1 there. So that's t squared, t, and 1. Okay, what I'm going to do now is I'm going to multiply that the first two matrices, and you'll see why in a minute. So, okay, if I multiply out, I've got 1 minus 14, that'll be minus 13 plus 9, so that'll be minus 4. Okay, I'm sure you know how to multiply matrices together. Minus 2 plus 14 is 12. 1, no, that's just going to be 1. Okay, 1 minus 10 is minus 9, plus 3 is going to be minus 6. Minus 2 add 10 is 8. And then we've got 1. Okay. So all I've done there is multiply the first two matrices together, and I've still got my matrix of t values. Okay, so I've got 2 by 3 multiplied by 3 by 1, so I'm going to end up with a 2 by 1. So I'm going to reach the calculator at this point. So what I've got minus 4 times 0.04 plus 12 times 0.2 plus 1. 3.24, and I've got minus 6 times 0.04 plus 8 times 0.2 plus 1. 2.36. Okay, so that's a point on my Bezier curve corresponding to t is equal to 0.2. So if I'm just going to graph that, 3.24 and 2.36 is around about there. Don't have to be too accurate. Okay, so for the next one, I'm going to calculate it when t is 0.4. Now, the only thing I've changed from the case when t was equal to 0.2, or the only thing which will change is this matrix here. These other two are going to remain the same. So there's no point in me writing those down because I've already calculated their product. Okay, so I'm going to just go straight to this step. Okay, so all I'm doing now is copying out what this matrix was. No point redoing the work. Can you see that? Okay. No point doing more work than we have to. 0.4, so 0.4 squared is 0.16, 0.4 and 1. And we just got to multiply those two together, which off the top of my head I think is 5.16 and 3.24. That was off the top of my head, by the way. No, not buying it. Okay. Sometimes I get really gullible students who go, "Really, you did that?" No, I've got it over here.
I believe you, John.
Sorry?
I believe in you.
Oh, you got down in my estimation there, if you believe that. But you understand, basically it's just matrix multiplication, it's nothing too difficult. Okay, C is when t is equal to 0.6. So again, no point doing this or calculating this again because we've already done it. And 0.6 squared is 0.36, 0.6 and 1. And if you do that, you get 6.76 and 3.6. Can't read my writing now, so I'm going to have to do it. 3.64. So you can see as the value of t changes, even value along the Bezier curve also changes. And the last one's 0.8. And 0.8 squared is 0.64, 0.8 and 1. And that gives 8.04 and 3.56. So just straightforward matrix multiplication. If I mark these points on the axes, so we've got 5.16 and 3.24, so around about there. Again, I'm just not being entirely accurate. 6.76 and 3.64. Not too good at this. It's around about there. And finally, 8.04 should be about here, and 3.56 should just be about there. And if I take my ruler, join the dots, and that's my Bezier curve. Notice I didn't bother with t is equal to 0 or t is equal to 1 because that's just going to be the first and last point. Also notice it's quite jaggedy. The reason it's a jagged curve is because I've only used a few values of t. In practice, you use maybe 100 values of t to make it a nice smooth curve. Is there any sort of questions about that? No? Very straightforward, hopefully. Okay, so Bezier curves, quite straightforward. Once you've got the matrix equation, quite straightforward to actually calculate. A few properties of these. Bezier curve always begins at the first control point and ends at the last control point. Sometimes you'll want the Bezier curve to be a straight line. Okay, so for example, fonts. You go back to looking at S fonts, there is a couple of straight lines in it. So if you want the straight line, the control points have to be in a straight line themselves. The start and end of a Bezier curve is tangential to the start and end section of a control polygon. Now, the control polygon is a polygon which is made by just drawing around the, or using the control points as vertices of the polygon. So this start line, P0 to P1, what this property states is that the tangent to the Bezier curve is the same as the first line at the start and also at the end there. So the tangent of the Bezier curve at that point is the same as that line. Any Bezier curve can be split into two Bezier curves. So this one here, that's a single Bezier curve. Let's say I wanted to split that into two. I could define control points which would for the first half and control points for the second half. And the Bezier curve is contained within its control polygon. It doesn't escape. Okay, this is known as what's called the convex hull property. So if you see this curve here, at no point does it ever go outside of that grey polygon. Okay, here's a few examples. So I've sort of had a bit of a play with these. Okay, so this is a MATLAB. This is part of your assignment is similar to this, but all I've done here is looked at a few Bezier, cubic Bezier. Okay, so here's a sort of straightforward one. So 4 control points, the blue line gives you that loop. Okay, play around with where the control points are, and you can make all sorts of loop, things like that. If you have a sort of drawing packages, always have these Bezier curves there, so you can sort of click a few control points and it'll give you a smooth curve. Right, so your assignment 9, and I'll talk a bit more about this later on today, is I want you to draw that. You recognise that as a logo for the university. Okay, that is drawn in MATLAB using cubic Bezier curves. Okay, so that's what your assignment 9 is. To get a pass on your assignment 9, I want you to just draw a single arrowhead. And I haven't got time now, but in one of the later lectures, I'll explain how I've done this. Okay, so this is actually made up of 8 separate Bezier curves. So 4 for the outside, 4 for the inside. Okay, so that's an arrowhead. If you want to get a merit, you stick 6 arrowheads together. Okay, so there's that's my original arrowhead. So this one here, notice it's sort of between -1 and 1, okay, in both directions, okay. So that's my initial one. All I've done is applied translation, moved it up, it's giving me that one. Then I've rotated it and moved it to there, and that one, and that one. Okay, so once you've got the initial arrow, all you do is copy it and move it. You've done that for assignment 3, way back in the first term. And finally, just shade it in. Okay. And then you've got the logo. Okay, in the next lecture, we'll be looking at going to 3D. Time's up now, so I'll cover this Bezier surface in the next lecture. Before we go, are there any questions on this? No. Okay.